Hello and welcome to our video on how theoretical physics can be used to explain the movie Tenet. In this video, we'll explore the concepts of time reversal symmetry, the arrow of time, time inversion, entropy, and paradoxes. And we'll see how they relate to the science fiction thriller Tenet. So we'll explore how theoretical physics can be used to explain the concepts and paradoxes that are presented in the movie Tenet. We'll first discuss the time reversal symmetry, and then we'll talk about the arrow of time, which are the fundamental concepts in the study of time. We'll then dive into the time inversion and entropy, which are closely related to the concepts that are presented in the film. And finally, we'll examine the paradoxes that arise when interacting with one's past self and the mathematical expressions that describe them. So overall, this video will provide a deep dive into the physics behind the movie Tenet, and it will shed light on how the concepts that are presented in the movie relate to the fundamental principles of theoretical physics. So for those who are living under a rock, Tenet is a 2020 science fiction action thriller film that is written and directed by Christopher Nolan. The film features the concept of time inversion, where certain objects and individuals are able to move backwards in time. The idea of time inversion in the movie is a fascinating one, and it has captured the imaginations of both physicists and the general public. Now, in this video, we'll explore that science that is behind the concept of time inversion and how it relates to the movie Tenet. So let's start with the concept of time reversal symmetry. And this concept of time reversal symmetry is a fundamental concept in theoretical physics. It is the idea that the laws of physics remain the same whether time is moving forwards or backwards, right? So there is no change in how physics works whether time moves forward or it moves backwards. In other words, if we were to reverse the direction of time, we would still see the same physical processes occurring. Now, I'll tell you one of the most famous examples of this time reversal symmetry is of a billiards balls on a pool table. Right, so imagine that this is your table, and here you have some balls that are sitting on this table, and with your stick you hit this white ball, for example, and then it is going to collide with all of these balls, and these balls then they will start moving. When that motion happens, right, we would the balls would move, and if we were to say record this game of pool and then we play it backwards, right? So you recorded the game and then you played it from the end to start, right? So you are basically reversing. So what you would see is that the balls they would be moving in a way that is consistent with the laws of physics, right? So you would see them moving exactly in the same way as they were moving. By the same way, I mean with the same physics that they initially moved, and then when they're moving backwards in time, so to speak, they would be moving consistent with the laws of physics. But here's the kick that, however, not all of these physical processes are time reversal symmetric, right? And I can give you another example for that, and that is if suppose you were to record a video of breaking an egg and then play it backwards. Maybe do this experiment. You're going to have to break an egg, but do this experiment, record a video of you breaking an egg, and then try to play it backwards. You would immediately know that something is amiss in the video, right? Now, let's talk about the mathematics of this time reversal symmetry. So I'm going to move a bit down. Let's start from here, right? So in mathematics, time reversal is done by an operator, right? So time reversal has what we call an operator. So this operator does an operation on what we call the state of the system, right? The state of the system is a function in mathematics. We call it the wave function, and it describes everything about the system. So it is telling you the complete state of system. So if you know a wave function or the state of the system, then you know what you're talking about, right? So any system that we can have, for example, breaking an egg. So egg is your system, right? And similarly, when you're striking these balls on the pool table, they are your system, and you can specify a wave function to that system. So that wave function is specifying a state of that system. And that wave function in physics and mathematics is represented with this symbol psi, and it's a function of the position of the ball, for example, and time, right? So how in time is that ball moving? So when this is the time, where is the ball, right? So position and time are also, well, linked, but they are the variables of this function phi, which is again the state function of the system. It describes the state. And in the language of quantum mechanics, it's also called the quantum state of the system, right? And that is, so to speak, if you're talking about subatomic particles, right? If these balls were subatomic particles, then this would be a quantum state of the system. Anyhow, the time reversal operation is done by an operator called T. And we usually write this hat-like thing on top of it. And this hat-like thing on top of it tells you that this is an operator. Now, the time reversal operator is denoted by this T hat, and it is defined as the operator that reverses the direction of time. So now, suppose that this phi of x comma t is a wave function that describes the state of a system at some position x and time t. Then the time reversed wave function will be given by, so under time reversal, your wave function would be given by phi, and then you take the complex conjugate of this thing. Now, if you're watching a video on the physics of Tenet, then you would have some basic knowledge of physics and mathematics. I'm going to assume that, right? And if you have some basic knowledge of physics and mathematics, then you know your complex numbers. You might have a very basic idea of complex numbers, where you also study what is a conjugate variable in complex numbers, right? So I'm going to assume that you have that knowledge. And so under time reversal, the wave function is a conjugate, and because we're reversing time, this is the position stays the same, but time is being reversed. So you add a minus sign with the time variable, right? So that tells you that there has been time reversal operation has happened, right? So again, this asterisk denotes the complex conjugation. Now, you can see immediately how this time reversal operator then acts. So if I take a state, if I take my system and I act the time reversal operator on my system, then this thing just becomes this wave function, the complex conjugated wave function, x comma minus t, right? Now, it's important also to note that this time reversal operator, this t hat, is a unitary operator. What does that mean? It means that it preserves the linear product of the two wave functions. So what does that mean? That means that if I have a product of two wave functions, phi 1, suppose you have two systems, right? And the other one is phi 2, and you're taking the product of those two systems, you're multiplying those two states, then this is exactly the same as, or you can read it the other way around, that if I were to take t hat on my wave function 1, and I were to multiply it with t hat on my wave function 2, then I would get back the same thing, right? So what does this mean? This implies that if a system is invariant under a time reversal, its wave function will satisfy a particular condition, and that condition is that your wave function psi of x comma minus t should be equal to t hat time reversal acting on the state x comma t, right? And then you can write this in terms of a phase, right? This is how we talk in the language of physics and mathematics. And this thing, when acts on this thing, again, it being t hat being unitary, this is iota, this is the complex iota, and then you have theta, where theta is your phase factor, right? And then you have your original state psi of x comma t. Right. So that is more or less the mathematics of time reversal. We're not going to go any deeper into the mathematics of this concept now. We're going to move now and talk about the concept of the arrow of time. Now, this concept of arrow of time is closely related to what we were just talking about, the time reversal symmetry. Now, the arrow of time refers to the idea that time only moves in one direction, that is forward, right? That's why you call it the arrow of time. So the arrow of time, suppose that this is the arrow and it's just moving in one direction, right? It's moving forwards. And well, this is because there are certain processes that are irreversible. What does that mean? That means that they can only occur in one direction of time, right? If you reverse the time, the process cannot go back to its original state. Examples of some irreversible processes includes the mixing of cream and coffee, or the melting of an ice cube, and also the shattering of a glass, right? Now, the arrow of time is a central concept in this movie, Tenet, right? Now, the time reversal or the time inverted objects and individuals in this movie are able to move backwards in time, effectively reversing the arrow of time. However, as we will see in this video, this concept is not without its flaws from a physics point of view. The arrow of time refers to the fact that time flows in a particular direction, and that is from the past to the future, right? So it flows in a particular direction, that is from the past to the future, and this is a consequence of the second law of thermodynamics. What is the second law of thermodynamics? So let me write it down over here. The second law of thermodynamics. And the second law of thermodynamics states that the entropy of a closed system can only increase over time. So entropy, we denote it with this symbol S, right? Now, what is this entropy? It is simply a measure of the disorderedness or randomness of a system. It measures how much randomness is there in a system or how disordered is your system, right? So for example, if you have something that is very well neatly arranged, so suppose these are the balls that are neatly arranged, and then you have another thing where the balls are lying everywhere. In these two cases, let's call this 1 and 2, the disorderedness or the randomness of a system is in this 2, right? Is in this example, is in this picture. While in the picture 1, they are rather more arranged in a very well manner, right? So the entropy is higher in the second picture compared to the first one, right? Now, mathematically, I can write the second law of thermodynamics as that the change in entropy should always be greater than or equal to 0. So either the entropy does not change for a closed system or the entropy increases. The change is always positive, right? So that means that the second law of thermodynamics implies that the universe as a whole is becoming more and more disordered over time, right? All right. So with that, we can further move on to the topic of the time inversion in this movie Tenet. So in the movie Tenet, certain objects and individuals have the ability to move backwards in time. And this thing, as we have seen, or as we have a little bit of understanding by now in this video, this is achieved through a process known as time inversion. So according to the movie storyline, time inversion is achieved by using a machine called turnstile, right? This is again according to the movie storyline, right? So these are not real facts that it can be, time inversion can be achieved by some machine that is called the turnstile. This is just completely according to the movie storyline. Now, the turnstile is able to invert the entropy of an object or individual. Effectively, it sends them backwards in time. So that's how they're going back in time. Now, the concept of time inversion is definitely an interesting one, and it raises many questions about the nature of time and the laws of physics. However, there are several flaws in the way time inversion is depicted in the movie from a physics point of view. Now, let's talk about that. We're going to discuss, by the way, the violation of the second law of thermodynamics as well in a bit. But now, the concept of time inversion is closely related to time reversal symmetry, right? So this is one thing that I have said multiple times, so just keep that in your mind. Now, in time inversion, the direction of time is reversed, right? So remember, that's exactly what was happening in time reversal symmetry. Now, in time inversion, because the direction of time is reversed, the events unfold backwards in time. This is different from time reversal symmetry, right? So you see that there is a difference coming up, and time reversal symmetry, which simply reverses the direction of time but does not change the order of events, right? Now, in time inversion, I can write it mathematically as your time t goes to minus t. So what does that mean? Remember, we can specify our system as the state phi of t, right? That's how you can specify your system. So if a system is invariant under time inversion, its wave function will satisfy this condition that I'm going to write, that this wave function phi of minus t is equal to the time reversal operator acting on this wave function psi of t, which is just e raised to power I theta times psi of t. This thing we have already seen before as well. This theta is just a phase factor. All right, now let's talk about the violation of the second law of thermodynamics in this film. So one of the flaws in the concept of time inversion in Tenet is that it violates the second law of thermodynamics. So again, Tenet violates second law of thermodynamics, right? So that's one thing. So let's talk about that thing. The second law of thermodynamics, as I have already stated, it states that the entropy of a closed system delta S will be always greater than or equal to 0. That means that the entropy of a closed system always increases over time. So what is entropy? Entropy is just the disorderedness of a system, right? So, well, in other words, you can say that the second law of thermodynamics tells us that things tend to get more disordered and random over time. So in the movie Tenet, the process of time inversion involves the inversion of entropy. What does that mean? It means that the objects and the individuals are effectively becoming less disordered and more ordered as they move backwards in time. So what does that mean? Immediately, having the knowledge of what we have talked about so far, it should tell you that this violates the second law of thermodynamics. Again, what's happening? The objects and the individuals are becoming less disordered and more ordered instead as they move backwards in time. So, but the second law of thermodynamics states that they should be getting more disordered, right? The entropy should increase, which means that this thing that is happening, it is violating the second law of thermodynamics, right? And so you know that the entropy, we can also, by the way, write this this entropy S, right? So this was the change in entropy, right? So this is what when we were talking about the change in entropy. But what is entropy mathematically? So entropy mathematically is written as minus K subscript B. This K subscript B is the Boltzmann constant, right? So it's just a constant, that it's just some number that scales what I'm going to write next. And then this is multiplied with this thing that you sum over all I of pi ln pi. Okay, now you might be wondering, what are these things that I have written? Well, kb is just a constant, and you can think of it as it is scaling this or whatever is next in front of it. This symbol that I wrote, it says that sum over all i's, right? And then you have pi ln is natural logarithm, right? And again pi. What is pi? It is the probability of the system being in the ith microstate. So again, you can think of microstate as the state of the system, and the ith microstate means that there could be many states that a system can be in. For example, I'm just going to give you a very simple example. If you think of a switch, then you can either have it as on or off, right? So that is, those are your two microstates, right? Similarly, you can have a coin toss where you can have heads, tails, heads, and tails. So what are you doing? You're tossing two coins and you're measuring the result. So these are the only possibilities that you can have from two coins. So what are these? All of them are the microstates, the possible microstates of that system. So in that same sense, this pi, the I is the microstate, pi is the probability of that microstate. So what is the probability that when I toss two coins, I get heads and tails? So I can measure that probability and I can assign it as pi, right? So that's basically what this equation is telling you. And this thing measures the entropy. This tells you, or this defines the disorderedness of the system. All right, now let's talk about some of the paradoxes in the film. Well, this violation of second law of thermodynamics is really also a paradox, right? Because what they're portraying, that is violating the second law of thermodynamics. So you can say that it is also a paradox. But anyhow, another flaw in the concept of time inversion is the potential of paradoxes, right? So you can have a lot of paradoxes. Now, what is a paradox, by the way? A paradox is a situation where the outcome of an event is contradictory or impossible. So in the case of time inversion, paradoxes can arise when an object or individual interacts with their past self. Now, in this movie Tenet, the protagonist is able to interact with his past self while moving backwards in time. However, this interaction creates a paradox, as the actions of the past self can affect the outcome of the present self's mission. This raises a question of whether it is possible to change the past, and if so, what are the consequences for the present and the future? Now, paradoxes can arise in time inversion when an object or an individual interacts with their past self, right? Now, you can write, it's not really a mathematical expression for a paradox, but you can say for a paradox, the outcome is contradictory or inconsistent. Right. So in the case of time travel, paradoxes can arise when events that have already happened are changed, or when events in the future affect the past. So these paradoxes, they violate what is called the principle of causality. And what is the principle of causality? The principle of causality simply states that an effect cannot occur before its cause, right? So suppose that a bottle falls. It cannot just have fallen and after that fall happened, you pushed the bottle off the table. That doesn't seem right? But it's because it isn't. So that's what principle of causality states, that the ball or the bottle falls off the table because I pushed, for example, I pushed that bottle off the table, right? So again, it states that an effect cannot occur before its cause. So the effect was the bottle fell and broke, and the cause was that I pushed the bottle. So the cause happened before, not the effect, right? So that is basically, well, it is one of the paradoxes in time travel. The other paradox that we can talk about is the grandfather paradox. Now, the grandfather paradox is a famous time travel paradox that arises when a person travels back in time and they kill their own grandfather. What does that do? That prevents their own existence, right? So they kill their own grandfather before the grandfather could birth their father. That would obviously prevent their own existence. So this again creates a paradox, as the person could not have traveled back in time to kill their grandfather if they were never even born, right? So the grandfather paradox is a violation of causality, as the effect, which is the person's existence, precedes the cause, which is the person's birth, right? So that's your grandfather paradox. Now, let's go back to the top and let's talk about, let's just basically close this video by discussing or giving some concluding remarks. So first of all, let's start with this thing, that the concept of time inversion in the movie Tenet raises many interesting questions about the nature of time and laws of physics, as we have seen some of those questions. While the idea of time inversion does seem or is fascinating, there are several flaws in its depiction in the movie from a physics point of view. The violation of second law of thermodynamics and the potential paradoxes that we have discussed are just a few examples of the problems that arise when time inversion is explored in a scientific context. Nevertheless, Tenet has succeeded in capturing the public's imagination and bringing the concept of time inversion to the forefront of popular culture. So in this video, we have explored the concept of time inversion in Tenet from a physics perspective, or a mathematical physics perspective. We have discussed the fundamental concepts of time reversal symmetry and the arrow of time, as well as the flaws in the concept of time inversion that were depicted in the movie. While there are several scientific inaccuracies in the movie's portrayal of time inversion, it has succeeded in sparking the public's interest in the concept and opening up a fascinating area of inquiry for physicists and moviegoers alike.